This is your presenter Asloob Mudassar, and I am presenting slide number 142 of the course on the laser physics. But here, since this slide is much longer, I shall only be presenting part A of this slide. So I am presenting part A of the slide number 142. The question is, what are solid state lasers? Describe important lasers of this category. The answer is solid state, dye and semiconductor lasers fall in the category of high density active media. Here we first describe the solid state lasers. In the solid state lasers, ions as impurity are introduced in a host material. So this is the critical point of this laser, that ions are as impurity are introduced in a host material. Active impurity ions either belong to rare earth or transition metal ions. Rare earth elements include neodymium, holmium, erbium, thulium, ytterbium. If the electronic configuration of xenon, that is in terms of krypton, that is the krypton configuration, electronic configuration of krypton, and along with, if we write 4d10, 5s2, 5p6, then it becomes the electronic configuration of the xenon. So this is used, if we use this as a reference, the electronic configuration of the rare earth elements can be expressed as, for example, for the neodymium, we can write the electronic configuration of the neodymium. This curly bracket represents that we are talking about the electronic configuration. So the electronic configuration of the neodymium can be given in terms of the electronic configuration of the xenon along with 4f4, 6d0 and 4s2. Similarly, for the holmium, the electronic configuration can be written as the electronic configuration of the xenon, and along with we can write 4f11, 6p0, 4s2. Similarly, for the erbium, we can write the electronic configuration of the erbium in terms of the electronic configuration of the xenon, and along with we can write 4f12, 6d0, and 6s2. And for the thulium, the electronic configuration of the thulium can be written as the electronic configuration of the xenon, and along with we have 4f13, 6d0 and 6s2. And similarly, for the ytterbium, the electronic configuration of the ytterbium can be written as the electronic configuration of the xenon, and along with we can write 4f14, 6d0 and 6s2. So you see that we have written, these are the rare earth elements: neodymium, holmium, erbium, thulium, and ytterbium. And we have expressed their electronic configurations in terms of the electronic configurations of the xenon. And you know that the atomic number of xenon is 54. So since xenon has a closed shell, so that's why we have written the electronic configuration of these rare earth elements in terms of the electronic configuration of the xenons. And you see that here you can see that a common factor is that 6d0 will appear in the electronic configuration of all these rare earth elements. So we can write that 4fn, 6d0, 6s2 with, if n is equal to 11, then it means that we are talking about the holmium. If n is equal to 12, we are talking about the electronic configuration of the erbium. If n is equal to 13, it means that we are talking about the electronic configuration of the thulium, that is the last three the last three orbits. And similarly, when n is equal to 14, that is for ytterbium, we can have this. So if you plug in capital N 11, 12, 13, 14 in this form, that is the last three orbital configurations, then we can obtain the electronic configurations for the holmium, erbium, thulium, and ytterbium. And you know that all these are rare earth elements. Similarly, in terms of the argon electronic configuration as the reference, the electronic configuration of the transition metal ions can be expressed as. So you see that here in the previous page, we represented the electronic configuration of the rare earth elements. Now we are going to represent the electronic configuration of the transition metal ions. But here we are going to represent the electronic configuration of the transition metal ions in terms of the electronic configuration of the argon. And argon has complete shell with the atomic number Z is equal to 18. So the electronic configuration of the chromium Cr is given as electronic configuration of the argon, and along with we can write D, 3D5 and 4s1. So in the chromium, we have, in addition to argon electronic configuration, we have 3d5 orbital and the 4s1 orbital. For the titanium, represented as a Ti, the electronic configuration in terms of the organ is the electronic configuration of the organ, and along with that we have 3d2 and 4s2. That is, two electrons are in the d orbital and 2 electrons are in the s orbital. For the cobalt, the electronic configuration of the cobalt in terms of the electronic configuration of the organ is given as 3d7 4s2. That is, there are 7 electrons in the 3d orbitals and 2 electrons in the 4s orbital. For the nickel, the electronic configuration in terms of the organ electronic configuration is, that is the electronic that is the organ electronic configuration of the organ, and along that we are writing 3d8 and 4s2. That is, there are 8 electrons in the 3d orbitals and 2 electrons in the 4s orbitals. So these are 4 transition metal ions that we are presenting over here, and we are presenting their electronic configuration in terms of the electronic configuration of the argon atom. So the formula that we can use for these is the electronic configuration of the argon along with the 3dN and 4s2, where capital N can take the following values. So N is equal to 2 for the titanium, N is equal to 7 for the cobalt, N is equal to 8 for the nickel. So if you substitute the value of 2, 7 and 8 over here in this formula, you can obtain the electronic configuration of the titanium, cobalt and nickel respectively. And these are the transition metal ions. So you see that here we have discussed the two metal ions here. One is the one is the rare earth elements that we have discussed, and the other category is the transition metal ions, and we have discussed 4 of them. And these will be used as the as impurity elements in the form of ions, which we shall be discussing soon. Most common Haas crystals includes oxides, which is aluminium oxide Al2O3, or fluorides, for example, YlIF4, or simply written as YlF. So this is the ytterbium lithium fluoride, which can be abbreviated as YL4. So here we have aluminium 3 plus being as an ion being too small can only accommodate transition metal ions, whereas ytterbium ion in Y3Al5O12 can accommodate rare earth ions. So you see that our host materials are the main host materials. There are 2 categories. Number 1 are the oxides, Al2O3. So this will be used. This host material can accommodate only Al3 plus ions, because this ion is too small and we can accommodate it over here. And the second category of the host material is fluorides, which are typically 2 of them, which is YlIF4 or YlF. and these can accommodate transition metal ions. So why? So aluminium 3 plus being too small can only accommodate transition metal ions, whereas Y3 plus ytterbium ion in Y3Al5O12 can accommodate rare earth element ions. So we have Al2O3 as the popular host material, and over here we have Y3Al5O12 as the popular host material for the rare earth elements or the rare earth ions, and we shall be discussing them in detail. Other important combinations are lithium, strontium, aluminium, fluorine, so abbreviated as LISAF, LISAF, is used as a host material for chromium ions, chromium 3 plus ions. Similarly, lithium, calcium, aluminium, fluorine, abbreviated as LiCaf, is used as a host material for chromium 3 plus ion. Alexandrite stands as a host material for chromium 3 plus ion. YLF stands as the host material for the rare earth elements. Similarly, YVO4 stands as a host material for neodymium 3 plus. So you see that we have represented over here different types of host materials. Some of them are host materials for the chromium 3 plus ions, and some of them are the host materials for the rare earth elements, and also for the neodymium plus 3. Here you can see that the neodymium and the other these four elements are the rare earth elements. So for these elements, the host materials have been presented as YLF and YVO4, whereas the host materials for the other elements for the transition metal ions elements, especially chromium, out of them the chromium is the most important, and for the chromium the host elements are LiSAF and LiCaf, and also the alexandrite can stand as the host material for the chromium plus 3 ions. So we have mentioned host materials for the chromium 3 plus ions, for the rare earth elements, and for the neodymium 3 plus ions. So YVO4 is specific for the neodymium 3 plus ion, whereas YLF can act as a host material for all the rare earth elements. And all these rare earth elements are these neodymium and holmium, erbium, thulium, and ytterbium. When a rare earth element is substituted into a host material, then two 6s electrons and one 4f electrons are used in the electronic binding. And the rare earth element is used as a triply ionized, that is Nd3 plus, holmium 3 plus, erbium 3 plus, thulium 3 plus, ytterbium 3 plus. So you see that these are the ions from the rare earth elements which are used in the ionic bonding, and 2s and 2 of the 6s electrons and 1 of the 4s electrons from the electronic configurations of these rare earth elements acting as these ions can act in the ionic bonding of in the host materials. The rest of the 4f electrons arrange themselves in such a way that a large number of energy levels are created. For example, in the electronic configuration, you can see that we are talking about that two 6s electrons and one 4f electron will contribute. So two 6s electrons from each of these and one f electron from 4f electrons will contribute. So these 6 electrons will contribute in the electronic configurations. in the binding of when these are substituted as an impurity in the host materials, then of course these three electrons, two 6s electrons and one 4f electrons from each of these can act as a contributing towards the ionic bonding. So here I have mentioned that when a rare earth element is substituted into a host material, then two 6s electrons and one 4f electron are used in the ionic bonding, and the rare earth element is used as triply ionized. The rest of the 4f electrons arrange themselves in such a way that a large number of energy levels are created. So you see that these three electrons will contribute in the ionic bonding. And you see that there are many other electrons will be left in the 4f subshells. That is, for example, if one F will contribute in the electronic bonding, then there will be 3f electrons left in the neodymium. Similarly, 10 electrons will be left in the 4f orbital. 11 electrons will be left in the 4f orbitals. 12 electrons will be left in the 4f. 13 electrons will be left in the 4f of the ytterbium, because three of them will be contributing towards the ionic bonding in the host material. The creation of these energy levels is due to three types of interactions. Now you see that when we have added these impurities, these active impurities, for example, either we have added a neodymium ion or the holmium ion or the erbium ion or the thorium ion or the ytterbium ion. If one of them is used as an active contribution, as an active material in the host material, then you see that we have a large number of energy levels are created by the 4f, by the electrons which are left in the 4f subshells. So the rest of the 4f electrons arrange themselves in such a way that a large number of energy levels are created. So the creation of the large number of energy levels will be due to the number of electrons left in the 4f orbitals. The creation of these energy levels is due to three types of interactions. Coulomb interaction among the 4f electrons. So this is one of the reasons that the energy levels are created, because of the Coulomb interaction among the 4f electrons. The second is spin orbit coupling. That is, the spin angular momentum will interact with the orbital angular momentum of the system, and due to the spin orbital coupling, the further the electronic configurations or the electronic levels are created. And the third one is the crystal field interaction. So the crystal field can also interact with these subshells and result in the formation of the energy levels, which we are now going to explain. The 4f states are split into sublevels with a separation of the order of 10,000 centimeter inverse. Each of these sublevels is further split into more levels with a typical separation of the order of 3000 centimeter inverse. The weakest perturbation due to the crystal field interaction further split them with a typical separation of the order of 200 centimeter inverse. The main cause of this weak perturbation is the shielding of the nuclear charge by the screening effect of 5s2 and 5p6 orbitals. So you see that now we have described three types of interactions. Coulomb interactions among the 4f electrons, spin orbit interactions, crystal field interactions, but the main separation of the energy levels will be due to the Coulomb interaction among the 4f levels, and the order of magnitude of separation is of the order of 10,000 centimeter inverse. The second stronger interaction is the spin orbit coupling. And due to this spin orbit coupling, each of the sublevels which were split due to the Coulomb interaction, each of these sublevels is further split into more levels with a typical separation of the order of 3000 centimeter inverse. and each of these sublevels will undergo inter-weak perturbation due to the crystal field interactions and will further split with a typical separation of the order of 200 centimeter inverse. The main cause of this weak perturbation is the shielding of the nuclear charge by the screening effect of 5s2 and 5p6 orbitals. So where are these 5s2 and 5p6? So you see that I have represented the electronic configuration of these rare earth elements in terms of the xenon electronic configuration. And if you look at the xenon electronic configuration, which is written in terms of the krypton, is electronic configuration of krypton along with 4d10, 5s2 and 5p6. So consider these two last, which is 5s2 and 5p6. So actually these are the complete filled orbitals. For example, 4d10 is also completely filled orbital, 5s2 is also a completely filled suborbitals, and similarly 5p6 is also a completely filled orbital. So you see that for example, just let's talk about the last two, which is 5s2 and 5p6. These two orbitals actually are responsible for the shielding of the nuclear charge. So we can say that the main cause of this weak perturbation is the shielding of nuclear charge by the screening effect of 5s2 and 5p6 orbitals. The 4f4f transition are parity forbidden. So let me explain to you. For example, since we are talking about these rare earth elements as an active impurity ions, because you see that these will contribute in the form of triply ionized ions, will contribute as in the ionic process of with the host material, and then you see that we are left with only 4f electrons. For example, 2s electron and 4f electron will contribute in the ionic bonding. That is the 3 electrons from each of these. And then you know that, for example, 3 electrons will be left over here, 10 electrons will be left in the holmium, 11 electrons will be left in the erbium, 12 electrons will be left in the thulium, and 13 electrons will be left in the ytterbium, when these will be used separately as an active impurity ions in the host materials. So it means that now there will be an interaction with the, since 4f can also interact with each other. So that's why we are talking about over here that the 4f transitions are parity forbidden because they have the same parity. For example, if the parity is even, then both will have the even parity. If the parity is odd, then both will have the odd parity. And since the parity is the same, so it is a parity forbidden transition, or you can say that it is a very weakly allowed transition. So the 4f transitions are parity forbidden, but the wave functions due to the crystal field interaction have opposite parity. And thus the radiative transition with weak probability are possible with a lifetime of the order of 100 microsecond. So let me read again. The 4f transitions are parity forbidden, but the wave functions due to the crystal field interaction have opposite parity. And because of the opposite parity, the transitions will be allowed. And thus the radiative transitions with weak probability are possible with a lifetime of the order of 100 microsecond. Due to the screening effect, there is a weak coupling between the electrons and phonons. So, due to this screening effect, as I have explained that how the screening is done, the screening is performed by the 5s2 and 5p6 orbitals. So due to the screening effect, there is a weak coupling between the electrons and phonons, which is non-radiative for low ion doping. There is another non-radiative decay process due to the ion-ion interaction at high doping concentration. So you see that here we have two types of non-radiative decay. One is due to the weak coupling between the electrons and the phonons, and the second is that this interaction or non-radiative decay is possible for low ion doping. Now there is another non-radiative decay process, and this is due to the ion-ion interactions at high doping concentrations. So when the doping is very high, then the ion-ion interactions will result in a non-radiative decay process. The threshold pump rate is proportional to 1 over sigma tau. This has been discussed in one of the previous slides on the course. The threshold pump rate is proportional to 1 over sigma tau. So this threshold value is reduced due to large lifetime tau. So tau is large and sigma is the peak cross section. And the relationship is valid for laser systems similar to a 4-level laser systems. So you see that in the 4-level laser system, we have observed that the lifetime tau is larger. And that's why similarly, the same thing happens over here, that the lifetime tau of the upper state is much larger and similar to the case of a 4-level laser system. So you see that here I have explained that the 4f electrons which are left after the impurity element interact ionically with the host material, contributing 3 electrons, 2 s electrons and 1 4f electrons, and then you see that the electrons which are left in the active impurity are the 4f electrons. They could vary according to the impurity we are talking about. For example, in the if we are talking, you see that there are different number of electrons in the 4f orbitals according to the value of according to the name of the impurity. So depending upon the nature of the impurity, many electrons will be present in the 4f orbitals, and these 4f orbitals will interact with each other. But you see that since the interaction of the 4f transitions are parity forbidden, or we can say that these are weakly allowed transitions. But you know that the wave functions due to the crystal field interaction have opposite parity, and thus the radiative transition with the weak probability are possible with a lifetime of the order of 100 microseconds. So the only so this enables us, that is the wave interaction due to the crystal field have opposite parity and enables the radiative transition. And due to the screening effect, there is a weak coupling between the electrons and phonons, which is non-radiative for low ion doping. There is another non-radiative decay process due to the ion-ion interaction at high doping concentrations. The threshold pump rate, which is proportional to 1 over sigma tau, is reduced due to large lifetime tau, where sigma is the peak cross section, and the relationship is valid for laser systems similar to 4-level laser system. So you see that as far as the rare earth elements as an active impurity elements are concerned, we have explained that how the 4f interaction results in the radiative transitions and also in the non-radiative transitions. Now we are talking about the next elements, which are the transition metal elements, and chromium out of them, that is chromium, titanium, copper, cobalt and nickel, and chromium is the most important element out of these, and we shall be talking about chromium mainly over here. So when chromium atom is added to an active impurity as an active impurity to an ionic crystal, 1 4s electron and 2 3d electrons contribute and the chromium is found as a triply ionized, that is Cr3 plus. And you can see that from these, one 4s electron will contribute and two 3d electrons will contribute. So in the ionic process, and the chromium will be triply ionized. Similarly, in the titanium, one 2s electrons and one 2 4s electrons and one 3d electrons will contribute in the ionic process. So chromium will appear as a triply ionized, and titanium will also appear as a triply ionized, but cobalt and nickel will appear as doubly ionized, because they will not contribute 3 electrons, they will contribute only 2 electrons in the ionic bonding. So when the chromium atom is added as an active impurity to an ionic crystal, one 4s electron and two 3d electrons contribute, and the chromium is found as triply ionized, that is Cr3 plus. The rest of the 3d electrons arrange themselves in a large number of states, which are 24 in chromium 3 plus ion. So you see that here chromium will contribute 3 electrons, one 4s electron and two 3d electrons in the ionic bonding when it will introduced as an active impurity element into a host material. And then you see that there will be three 3d electrons, three 3d electrons will be left, and these 3d electrons will of course will result in the formation of the energy levels. The rest of the 3d electrons arrange themselves in a large number of states, which are 24 for the case of chromium 3 plus ion. So you see that when the chromium is added as a triply ionized active impurity into a host, into an ionic crystal as a host material, then you see that the 3d electrons which are left in the chromium will contribute in a large number of states, which are 24 in number. All emission and absorption transitions are 3D transitions. The 3d electrons, because you see that when ionic bonding is formed by the chromium ion contributing as an triply ionized element, then of course you see that only the number of electrons which are left will be left in the 3d orbitals. And here for the case of the chromium, 3d electrons are left. The 3d electrons move in a strong crystal field of the host material and introduce vibronic character in the 3d transition. This widens the absorption and emission bands, like the 4f transitions that we have discussed for the case of rare earth elements. The 3d transitions are also parity forbidden, but they occur with greater frequency, but with a reduced lifetime, and the lifetime is of the order of a few microseconds, whereas the lifetime for the case of rare earth elements was of the order of 100 microsecond, whereas in case of chromium it is only a few microsecond, and thus the product sigma tau is also smaller, because tau will be smaller. Tau is smaller in case of chromium. When titanium Ti is added, it would be presented as a titanium triply ionized, that is as a titanium 3 plus ion, whereas cobalt and nickel will be doubly ionized. So out of these transition metal ions, chromium and titanium will contribute, if added as an active impurity into a ionic crystal, will contribute as triply ionized elements, whereas the cobalt and nickel will contribute as doubly ionized in a host material. So this is what I have explained, that when a titanium, that is Ti, is added, it would be presented as a titanium 3 plus, whereas cobalt and nickel will be doubly ionized. So chromium and titanium will contribute as triply ionized, whereas the cobalt and nickel will contribute as doubly ionized in an ionic crystal, while forming an ionic bond with the ionic crystals. There are different host materials: fluorides, oxides, crystals, glasses, etc. So these are the possible host materials: fluorides, oxides, crystals, glasses, etc., which have different physical properties. For example, oxides are harder with better thermal fracture limit. Fluorides show lower thermally induced by refringence and lensing effect. Glasses are easier to fabricate and are cheaper than crystals, but possess lower thermomechanical and thermo-optical properties. Among the glasses, silicates, for example, SiO2, phosphates, P2O5, silicates have better thermal and mechanical properties. Phosphates have better non-linear optical and thermo-optical properties. Important solid-state lasers include ruby laser, neodymium laser, which we call as ND-YAG or ND glass lasers, crystalline host lasers, ytterbium YAG laser, erbium YAG, ytterbium erbium glass lasers, holmium YAG lasers, fiber lasers, alexandrite laser, titanium sapphire lasers, chromium LiSAF lasers, chromium LiCAF lasers, etc., etc. So we are going, in the next few pages, we are going to discuss some of these important laser systems. And the next we are going to discuss will be the ruby laser, this one. And this will be discussed in part B of this presentation. So here, this is the end of part A of slide number 42.